Hello dear EAPCET aspirants, welcome back to NEET World. So we'll be continuing our discussion on solutions chapter. Okay, so in the last sessions we have covered types of solutions and how can we express the strength of solution, or I can say concentration of solutions, like concentration terms. So what is mean by molarity, molality, normality, mole fraction, all this we have discussed. And after that the solubility of particular substance, like solubility of gas in liquid, that is what explained by Henry's law right now. So these things we have discussed. After that the factors affecting vapor pressure and the factors affecting vapor pressure also covered right now, and numericals related to that topics are also covered, right? And after that we have discussed about ideal solutions, and particularly Raoult's law we discussed first, and then next ideal solutions and non-ideal solutions, right? I hope you have watched the previous sessions. Okay, so if you haven't watched those sessions, I suggest you to watch all the sessions that I have covered previously, so that it will be helpful for your preparation. Okay, right. And one more thing, today we will be discussing colligative properties. Okay, so you can expect a question from colligative properties in the exam. Okay, colligative properties are very important, whether it is NEET, JEE or EAPCET, these colligative properties are very important. And this is easy only, colligative properties. So it is easy to understand, you just follow the session so that you will get the complete clarity. I am going to explain the theory first, and also along with that I will show you the PYQs also that comes that is asked in the EAPCET as well as JEE and NEET exams. Okay, I will show you all those things. Wait, look at this first. Okay, and this particular session is more focusing on EAPCET aspirants also. Okay, right. If you are a serious EAPCET aspirant, just look into our previous videos that we are covering from last 20 days. Okay, right. If you like the content, just click on the subscribe button and you can share with your friends. Okay, so what exactly colligative properties? Tell me. See, this is a special property of dilute solutions. Which solutions I am saying? Dilute solutions, also considered as ideal solutions. Okay, ideal solution is a special property of ideal solutions. So what makes it to be special? See, the ideal solutions, in ideal solutions there are some properties like elevation in boiling point, osmotic pressure, depression in freezing point, all these things are there. These properties depend upon number of solute particles present in the solution. We know solution is made up of two components, I mean two parts. One is solute, other one is solvent, right? Now these are the two parts present in the solution, right? Right. So now what I am saying is colligative properties are the properties which depends on number of solute particles, present. Present in the solution, but not on their nature, It purely depends on what? Number of solute particles present in the solution, but not on the nature of solute or solvent here, but not on their nature. Okay, right. I will tell you what is this number of solute particles and all. For example, I am taking, you can consider 1 mole of a non-electrolyte, 1 mole of glucose you can consider, or urea you can consider, and 1 mole of an electrolytic solution you consider, 1 mole of NaCl you take. So now what happens is, initially when I am adding urea to a solvent like water you can say, we are going to get a urea solution right now. So in this urea solution, for example 1 liter of the solution is made. Okay, so now what happens, here we have urea solution right now, and here also I am adding NaCl salt. See, just be conscious for next 10 minutes so that you will get complete clarity on these colligative properties. Okay, right. So look at this, if I add NaCl to the same solvent, like same solvent I am taking, water you can say here solvent, to make 1 liter of this NaCl solution. Okay, what we have now? NaCl solution we have, and another one is urea solution we have. Right. Since urea is a non-electrolyte, whatever the number of moles of urea we have added, same number of moles of urea will be present in this. It means number of solute particles in this solution will be 1 mole only. But if I add NaCl, sodium chloride, what happens? It's a strong electrolyte, dissociates into or ionizes into Na plus and Cl minus right now. So now when we add 1 mole of this NaCl into this solvent to make this solution, now we will be having 2 moles of solute particle, 2 moles of solute particles. What are the 2 moles? 1 mole of Na plus particles and 1 mole of chloride ion particles right now. So it means what happened? Number of particles increased in the second case now. Now the colligative properties in the second case will be more, because more the number of particles, more will be the colligative properties. Okay. So now what I am saying, the first case I have added urea, that is non-electrolyte to make this solution, where there is no dissociation or association, therefore number of particles will be remains same as the number of particles you added. But I am adding initially same quantity as above, but since it is undergoing dissociation, therefore number of particles here observed. See, initially this is all considered as one particle, but in water it is undergoing ionization to form its respective ions. Therefore number of solute particles, 1 mole sodium ions, 1 mole chloride ions, total number of solute particle doubled here na. Therefore colligative properties also becomes almost double. Okay, I hope this explanation is clear, right? So if there is any blur on the screen, just please inform me in the chat box so that I will make it correct. Right, let me correct this first for some time. Yeah. Right. So next one. So what are the colligative properties now? What are the list of colligative properties we have here? So just look at here, list of colligative properties now. What are the important colligative properties we have? Properties. Okay. So first one here we have RLVP, relative lowering of vapor pressure, and second one is ΔTb, that is elevation in boiling point. Okay, and the third one here is ΔTb, I can indicate, use for indication of elevation in boiling point. The next, depression in freezing point. This is indicated with symbol ΔTf. Very easy, all these are just follow here. Next, osmotic pressure. Take pressure. Okay. Hope up to here it is clear. There are 4 colligative properties which are important as of our syllabus. One is RLVP, next elevation in boiling point, depression in freezing point, osmotic pressure indicated with symbol pi. Okay, right. So now what is the use of understanding this? See, using these colligative properties, we can able to find the molar masses of like biomolecules, polymers or macromolecules here. Particularly in case of biomolecules like proteins. Okay, so we can use like osmotic pressure for measuring their molar masses. Okay, if they give one unknown biomolecule or biopolymer and they are asking us to find its molar mass, so we can find that using a technique called osmometry. That is what? Osmotic pressure only. Okay, or osmosis here. Okay, right. Hope first 4 things are clear here. Let me explain one by one here. So first one is RLVP, relative lowering of vapor pressure. See, the name itself saying lowering of vapor pressure. It means what happening when we compare with the initial pressure, the pressure of the solution is reduced. Okay, so it means when a non-volatile solute, volatile solute is added, when a non-volatile solute, I am indicating with solute with NB, solute is added, the vapor pressure of solution or the solvent here, vapor pressure of solution decreases. Okay, so why it is decreases? See, when we are adding a non-volatile solute to a volatile solvent, to what we are adding? To a volatile solvent. So vapor pressure of this volatile solvent decreases now. So why it is? Look at here. Now what I am taking? I am taking a beaker containing solvent in this. So which solvent I am taking? So I am taking a volatile solvent. Volatile solvent means what? Volatile solvent means what? It will easily undergoes vaporization, right now. So it has more tendency to undergo vaporization. So here liquid, and here I am saying vapors of that solvent A. Solvent I am indicating with symbol A. Okay. So now what happens? I am saying it has more volatility. Okay. Therefore it converts into its vapors. Right now. So now to this we are adding a solute B which is non-volatile. Right now. If this is non-volatile, what happens? These solute particles now accumulates on the surface of this solvent. If it is accumulating like this, now what happens? So these solute particles which are non-volatile, that will decreases the vapor pressure of this solvent. Why it is decreasing? Because they are accumulating, or they are occupying the position at the surface, so that the escaping tendency of vapors of this solvent will be decreased now. Therefore vapor pressure decreases. Okay. If I say P naught is the initial vapor pressure of this solvent A. Okay. Now what happens here? It become a solution, right? So I am writing PS. So PS is the vapor pressure of this solution. So what is the lowered in the vapor pressure? That is what? Lowering of vapor pressure will be taken as P naught A minus PS. This is what? P naught A minus PS indicates what? Lowering of vapor pressure. And here as per the concept, it is relative lowering of vapor pressure. It means LVP by initial pressure, that is P naught A. That is nothing but P naught A here and P naught A minus PS here, that is it. So this is what? Relative lowering of vapor pressure. So this is what important here. This is the one which is colligative property. This is not the one here. RLVP is a colligative property, not LVP. Okay, right. And what is the thing you need to remember here is, now how can you calculate this RLVP, relative of lowering of vapor pressure, by looking at the amount of solute and solvent present. See, look at here, we have made a solution by mixing A and B right now. So I am saying B is solute, A is a solvent right now. So the number of moles of solute added indicated with NB, and number of moles of solvent added is indicated with Na. Okay, right. So now what I am saying here is, I am saying mole fractions. So mole fractions of AB means what? Number of moles of A by total number of moles, that indicates mole fraction of A. Similarly, number of moles of B by total number of moles indicates mole fraction of B right now, right. So now look at this, what I am saying, according to Raoult's Raoult's law, what we know? According to Raoult's law, P total or vapor pressure of solution is equals to vapor pressure of that component A plus vapor pressure of component B in the solution right now. So but we know here our B solute is a non-volatile. If something is non-volatile, its vapor pressure is considered almost equals to 0. Okay. So if this is equals to 0, whatever the amount of number of sols you might add, that decreases the vapor pressure of the solvent, but not having any difference here. So I can make this as 0. Therefore vapor pressure of solution will be now equals to PA only. Why I am saying PA? Because vapor pressure of solute will be equals to 0 now, because it is non-volatile. We have only volatile component, it is PA. Okay. So this PA we can write P naught A chi A. See guys, I can directly give the formula also, but if I give direct formula and if I do some 1-2 numericals, that will be also helpful. But what I am saying is, if I give complete derivation also, so that you will get the concept also. So that is my intention here first. That is why I am giving you the concept first. Okay. Now look at this. What I can write? PS will be equals to P naught A is there, and in the place of chi A I can write 1 minus chi B also, because sum of mole fractions are 1. So from these we can write PS equals to vapor pressure of solution equals to P naught A minus P naught A chi A right now. So again from these I can write P naught A minus Ps is equals to this one, P naught A Chi A. So again I can send this from here to here, that's it now. Yes, P naught A here, that's it. This is our Raoult's law. Okay, so it means this is our RLVP. Relative lowering of vapor pressure will be equals to mole fraction of solute, that's it. Okay, so RLVP will be equals to P naught A minus Ps by P naught A will be equals to number of moles of solute by total number of moles, Na plus Nb, that's it. Okay, while doing the numericals, you can ignore the number of moles of solute in denominator. Why we can ignore? Since it is a dilute solution, see Raoult's law, this RLVP colligative properties are applicable only in case of ideal solutions only. Okay, it means they should obey Raoult's law. So here I can say this is almost equals to Nb by Na. So all dilute solutions almost considered as ideal solutions. In case of dilute solutions, number of solute particles are very less now. Therefore, something bigger number plus something smaller number can be considered as there is not much change now. That's why I am taking Na plus Nb as Na itself, because this is very small. Nb is very small when we compare with Na. So in these cases we can take Nb by Na. Okay, hope this is clear. And one more thing here you need to know is see, whenever there is blur on the screen, please let us know in the chat box. Okay, right. So the next here we have elevation in boiling point. What is the next colligative property? Second one is elevation in boiling point. Okay, this is also very simple. So now what the name itself saying now, boiling point of the solution will be elevated by addition of solute. Okay, so now what happens when a non-volatile solute is added to the solvent, volatile solvent, its vapor pressure decreases and boiling point will increase now, because vapor pressure is decreasing, the boiling point increases. So boiling point increasing means that is what we can consider as elevation in its boiling point. So generally where we will be seeing this elevation in boiling point in our daily life? So while cooking rice, or while boiling the eggs, sometimes we used to add salt, right? So why we are adding salt there? Because whenever we add salt to the water, the boiling point of water will be elevated. Instead it is boiling at 100 degrees Celsius. Now it will boil at somewhat 101, 102 depending upon amount of salt you added. So if the boiling point of water increases, that egg will boil very perfectly right now than the previous case without salt and with salt. The boiling will be very proper in case of while addition of salt. Okay, because boiling point of water elevated, therefore egg boils to a better extent. Okay, right. So now how can you indicate this boiling point? Delta Tb, right? So now this delta Tb is directly proportional to its molal concentration, molality I can say. Okay, so more is the concentration, it means more is the number of moles of solute, greater is its elevation in the boiling point. So now how the graph will looks for this? See, I am drawing here vapor pressure versus temperature. So we know vapor pressure increases with increase in temperature. So if I am saying this is a vapor pressure of pure solvent. Okay, so it is reaching a point that is nothing but the 1 atm pressure. See, 1 atm pressure is nothing but the particular solvent reached its boiling point. Okay, so now what I am doing, I am adding a non-volatile solute. This is for pure solvent. To this solvent what we are doing now, I am adding non-volatile solute. So it becomes a solution now. So in this solution case, vapor pressure will be decreases and its boiling point increases, something like this. Okay, so what you are observing here, see at each point vapor pressure is decreased and boiling point, if you see, boiling point is raised. Initially this is at here, and after adding that solute, it becoming solution, boiling point is moved up to here. Initially it is at here, now it is moving up to here. It means what? Temperature is increased in the right. So that is what the elevation in boiling point. So now this difference is there now, you can indicate as delta Tb elevation in boiling point. So how can you write this delta Tb as equals to, this is a boiling point of solution, TBS I am saying, and this is a boiling point of pure solvent, this is T0B I am saying, that's it. Okay, T0B indicating boiling point of pure solvent and this is for solution. So that just take the difference of both, TBS minus TB0. This is the elevation boiling point formula or a difference you can take. So now here I have given two formulas. One is this is the difference of temperatures like elevated temperature, the solution minus boiling point of pure solvent. Right now. So now this delta Tb I can also write delta Tb is equals to, I am removing proportionality and writing a constant Kb. So Kb indicates molar elevation constant. What is that Kb? Molar elevation constant. Okay, multiplied with m, that's it. Delta Kb, delta Tb equals to Kbm. Okay, so now during solving the questions, what to do is, so take delta Tb is equals to solution boiling point will be equals to, see this is nothing but I can write this now, right. If I send minus to that side, it will become Tb0, it means solvent, pure solvent boiling point place you are adding this thing Kbm. It means if you add more amount of concentration, if you increase the more amount of solute, therefore their elevation boiling point will be increase in the boiling point solution will be greater, because solvent plus this added amount will be making it to be more in the boiling point, that's it. This is what you need to know here first. Okay, right. Let me show you one or two questions on these so that you will feel more confident. Look at this question. What they are saying, what is the boiling point of solution of 0.1 molal KCl? See, one more thing before going to numericals itself, I just want to add one more point. Therefore, you will get more clarity here itself. See, I told you colligative properties are depends on number of solute particles. If you observe here, we have KCl right now. So it's a KCl is a strong electrolyte, undergoes 100% dissociation as they mentioned. If it is undergoing 100% dissociation, we are going to get independent K plus ion and Cl minus ion in the aqueous solution. Therefore, number of solute particles now becoming how many? 2, right? Therefore, number of solute particles increasing means our colligative properties also become increased. Okay, if it is increased twice, colligative property also become doubled. Okay, so what you need to make here, delta Tb equals to, so we need to insert this number into our formula. So what is our formula? You have studied Kbm only right now. So now for identifying number of ions after dissociation or association, I am introducing a factor I that is called Van 't Hoff factor. So what is the use of this I? So I will be adjusting the number of particles or including the number of particles after undergoing association or dissociation in each case. So this is undergoing dissociation, so I value will be 2. Just take number of particles formed, that's it. So I can take here 2 into what is the Kb value mentioned, it is 0.52. See, this is a EAPCET question, 0.52, and what is the molality mentioned? Molality 0.1. Okay, so this is one thing they have given. And one more thing, if you observe, this is they are asking boiling point of solution. So boiling point of solution means what I told you, TBS will be equals to TBS minus TB0 will be equals to this one, because delta Tb is this one we can write. So from this TBS can be written as, I can send this that side. See, boiling point of solvent, what is our solvent here? Molar water here. Water is a solvent. Solvent water boiling point is 100 degrees. All of these are mentioned in Kelvin right now. So you can say 100 degrees Celsius plus 273. So this gives Kelvin. Temperature should be in Kelvin here. Okay. So what will be your answer? 373 plus this thing. So how much it is? So you can say 4 10 like this and 2 decimals, and here you have 0.1 means you can write 373 plus 0.104 right now. So if you observe, there are options having this kind of answer. So 373.104, yes, we have option number 2 as our answer for this particular question. Hope this is clear how easily we are solving this kind of questions. In the same way, I am going to give you one more model question for depression in freezing point. Okay, what we are discussing now, next point is depression in freezing point. Depression in freezing point we will discuss. Okay, let me check everything is going well or not. Right. Next thing is, in the same way you can able to solve for other things also, and just for making you more clear about this Van 't Hoff factor I have brought one more question here. So using this question you will get complete clarity on Van 't Hoff factor I. So what is the use of this Van 't Hoff factor? So by insertion of this Van 't Hoff factor I, we can get exact colligative property. If we are ignoring that I value, so we will get abnormal colligative property value, which is wrong because it depends upon number of particles. Okay, so for example, I have a compound A. Okay, so this compound A is a having in a polymeric form or some n number of A's are there. So it will undergoes dissociation to give this n number of A plus ions. Now initially how many are there? One particle is there, but after dissociation, I mean at time t0, at time t, what happens? Some of this will undergo dissociation, like alpha 1 minus alpha d I am writing, and this many number of particles are obtained right now. So now total number of particles, formed after dissociation, tell me how many are there? Just add, total number of ions will be equals to, add these two parts, 1 plus n alpha d minus alpha d. This I can write n minus 1 alpha d, that's it. So this will be the formula for finding total number of ions. Now Van 't Hoff factor I is there now. So this I means, I is nothing but total number of ions after dissociation, total number of ions taken initially, total number of ions taken initially, or total number of molecules you taken initially. That is nothing but initially we have taken only 1, so you write it 1, and total number of ions after dissociation are 1 plus n minus 1 alpha d, that's it. So just remember this sum will be equal to its Van 't Hoff factor, that's it. So I will be 1 plus n minus 1 alpha d. Okay, right. If they say only 60% dissociation, 40% dissociation, you need to put here. For example, 60% if they say, you use alpha d as 0.6. They say 40%, 0.4, like that. And what is this n represent number of ions? Okay, right. Now let us do it for this particular example. First of all, let me give you clarity using this NaCl. Okay, so NaCl after dissociation will get two particles, na, Na plus and Cl minus. So I value will be 1 plus, how many particles we have got? 2 now. So 2 minus 1, how many ions we got? 2 now. So 2 minus 1, and I am saying 100% dissociation. If it is 100% dissociation, you take alpha d as 1, that's it. So I will be 1 plus 1, so I value will be 2. So why it is 2? There are two particles here formed, that's it. Is this clear or not? I hope it is clear. Okay, if the same electrolyte, I am saying it is only undergoing partial dissociation of around some 60% dissociation it is undergoing. So what could be your answer? Alpha d becomes 0.6. Then I will be now 1 plus n. N is how much? 2 ions. 2 minus 1 into 0.6. It means 1 plus 0.6, you can say 1.6 will be your answer. So what you got here, if degree of dissociation is less, see, if degree of dissociation is less, the number of particles will also be less. Number of particles formed will also be less. Therefore, the Van 't Hoff factor is less and number of colligative properties will also be, the value of colligative property also less. Okay. So, here 2, here 1.6. So, colligative properties will be less in the second case. Okay. Right. Next, I will show you one more thing here. Can you solve this question? What they are saying? See, again EAPCET question, very easy, you can solve within seconds. See, what is Van 't Hoff factor for ferric sulfate? Assume 100% dissociation. First of all, tell me what is the formula of ferric sulfate? It is just Fe3 Fe2 SO4 3 times, that's it. Okay, ferric means iron should be in +3 oxidation state. Sulfate we know SO4 -2. So just crisscross, just multiply this number over here and this number over here, we will get this one. Okay, so this is the electrolyte. So now what happens, tell me, if I place this in the aqueous medium, water, what happens? It will undergoes dissociation to form ions. So what are the ions produced here? So 2 Fe plus 2 ions and 3 sulfate ions, SO4 2 minus ions. So tell me total number of ions formed. So 2 plus 3. So number of ions formed will be 5. Okay. So here you can see they mention 100% dissociation. It means I will be equals to 1 plus n minus 1 alpha d. Alpha d value degree of dissociation is 100% dissociation means. So in this case, what happens? You just check 1 plus n minus 1, minus 1 plus 1 is removed. So I will be equals to n. So I will be equals to how much here? So 2 plus 3, that is 5. That's it. This is how you can do if it is 100% dissociation. If it is only partial amount, they mentioned alpha is some sort 40, 60, 70 like that. You just multiply here with that number as 0.5, 0.6, whatever the percentage they have given. Okay. Hope this is clear. Right. If these things are clear, just click on like button and you can express your concerns or the difficulties you are facing in this particular topic in the chat box. I will be definitely discussing here. Okay. Right. See, I don't want to waste any student's time simply by discussing some unnecessary things. So just we'll be focused on the topic, we'll discuss some quality content along with some questions and then we'll finish up the session. Okay, right. I hope everything is going well here. If something is more you are expecting, you just mention in the chat box. Right. Next, let us move forward with few more questions. Look at this question. What they are saying here, see, when 20 grams of naphthoic acid is dissolved in 50 grams of benzene, okay, a freezing point depression of 2 Kelvin is observed. Again, we haven't discussed freezing point depression in freezing point now, so you can write ΔTf. Okay, what is this? ΔTf means the third colligative property, that is depression in freezing point. Okay, so what happens is when we add a non-volatile solute, in all the cases we are adding what? Non-volatile solute. So we are adding non-volatile solute to the non-volatile solvent. For what? We are adding to the volatile solvent. Now what happens, since it is a volatile solvent, it will be having more vapor pressure. So but whenever we add this non-volatile solute to this solvent, its vapor pressure decreases right now. So vapor pressure decreases, that's why we are saying its boiling point increasing, okay, and its freezing point decreases here. Okay, what I am saying, its freezing point decreases. Okay, so what do we mean by freezing point? The temperature at which vapor pressure of its solid will be equals to vapor pressure of its liquid. Okay, so this will be at this point, whatever the temperature we are measuring, that is considered as its freezing point. What is freezing point? The temperature at which vapor pressure of solid is equals to vapor pressure of liquid is considered as its freezing point. Now how can you draw the graph? Right, it's very simple. Look at here. as we have discussed vapor pressure versus temperature previously. So this is a curve for solvent, pure solvent, and this is a curve for pure, this is the curve for solution, and I am saying this is a 1 atm pressure here. Okay, right. These are the boiling points of solution and this solvent. Now what I am drawing is, see, I am extending this curve like this. Okay, so when I extending, this point indicates, see, this is solvent, we know, this is solution, we know, this is in liquid states. What is that? These are in liquid states. Okay, now what I am saying is, this is the freezing point. I am saying this is a freezing point of this solvent. Why I am saying freezing point? This is a curve, this is a vapor pressure curve for solid. So for solid also, if you observe, for solid solvent, vapor pressure increases with increase in temperature now. Yes, even it is having no vapor pressure or very less vapor pressure, that increases with increase in temperature, right? Right. So this is a point where we can say, this is a point where we can say the freezing point of Tf of pure solvent right now. So now just extend this solution curve also. Yes, extended. So here it is touching. So this is a freezing point of solution. That's it. Okay. So this both curves should be matched. I mean they should intersect. Then we can say it's a freezing point of solvent and solution. So what is the difference you are getting here? Delta Tf is equals to that higher value, that is Tf naught minus Tfs. This is indicating depression in freezing point. Hope this is clear, right? Next one. Here also depression in freezing point directly proportional to its molar concentration. Okay, I can remove that proportionality, I can replace with a symbol Kb, Kf here. Molar depression constant we can say, or cryoscopic constant we can call. Okay, like this we can write. So delta Tf means I can use this formula and this formula. So let us relate all those together. Delta Tf is equals to Tf naught minus Tfs, which is equals to Kfm. And I told you colligative properties are depends on number of solute particles. If any association or dissociation taking place, we will get different number of particles of solute right now. Therefore, it is mandatory to introduce Van de Graaff factor into the equation. I am introducing, right? Right. After this, what I can say, if someone asks you what is a freezing point of solution, now what happened? This is a freezing point of solution. Okay, or so Tfs will be equals to, now what happens? Tf naught, you just send this side and that bring that this side. So minus I Kfm. So what you are getting? So from the pure solvent freezing point temperature, you are removing something. Then we are getting our freezing point of solution temperature right now. So it means what? If more molar concentration, lower will be the freezing point. More amount of freezing point will be reduced, depressed I can say. If number of particles also increases, freezing point of solution decreases. You can remember because negative sign is there. Okay. So next step. I hope this is clear. Let us solve one question on this and we will move for the osmotic pressure. Once after completing that, we will solve all the colligative properties together so that you will get more clarity on the concept. Okay, right. Look at this question. This is from again 2021 TS EAPCET paper. So look at the question, what they are saying. The freezing point of an aqueous solution containing 25 grams of ethanol in 1000 grams of water. So given Kf is what? Cryoscopic constant. They are asking about freezing point of solution. That is nothing but delta Tf we have found just now. Tf naught minus Tfs is equals to IKFm. That's it. Okay. So ethanol is a non-electrolyte here. So you can say I value is equals to 1. And what about Kfm value mentioned here? 1.86. And what about molality mentioned? Molality given as 25 grams of ethanol solute in 1000 grams of water, that is nothing but 1 kg of water. So you can just write number of moles of solute, that is nothing but given weight by its molar mass. 25 by what is the molar mass of ethanol? Ethanol you write C2H5OH right now. So this is 24 and this is 5 and this is 16 and again this is 1. So 24, 30, 46. So you can take here 46, okay. And what is the weight of solvent given? 1000 grams, that is 1 kg now. So that is 1 by 1, that is over, okay. So this is what molality we got. So now they are asking this term. It means you can send this to that side. So that what happens? TFS is equals to TF naught minus 1.86 into 25 by 46. That's it. So TF naught is how much mentioned? See, it's an aqueous solution now. What is the freezing point of water? That is 0 degrees Celsius. If it is 0 degrees Celsius, you can put this. See, all the options are in 0, 0, 0 degrees. Directly you can take 0 degrees. If sometimes they mention in terms of Kelvin, instead of taking 0 degrees, you can take 273 Kelvin. If the options are in Kelvins, okay, 273 minus this thing, okay. Since it is 0 degrees, so this value becomes 0, okay, and this first term becomes 0. So 0 degrees, 0 degrees, and this will be almost 1.8 terms only, okay, 1.8 around that value, okay. So this will be around we can get around 1, okay. How much we are going to get? 1, okay. That's it. TFS, freezing point of solution, will be equals to now minus 1 degree Celsius will be your answer for this question, okay. TFS will be this much. Hope this is clear, and our option number 4 will be perfect answer for this question, okay. I hope it's not having blur. Right. I hope this question is clear, everything is clear. So now if the freezing point of solution is given in terms of Celsius, minus 1 will be your answer for this question. But if they ask in Kelvin degrees, so Kelvin scale, what will be your answer? TFS will be equals to 273 minus 1, that is 272 Kelvin you should say. This should be our answer in terms of Kelvin scale, okay. But here it is given in degrees Celsius, so fourth option will be your perfect answer for the question. Hope everything is clear, right. Let us move forward with few more concepts, and before moving to the next concept, next question, let me finish off the osmotic pressure also. So what exactly osmotic pressure means? See here, osmosis you understand first, okay. So look at this, I am drawing a container which are separated by a membrane. This membrane is called semi-permeable membrane, okay. And here I have two sides now. This membrane is separating the containers in these two parts. So in first part we have very dilute solution, this side is very dilute solution, or purely solvent might be there, pure solvent is there, and this side I have concentrated solution. Now what happens is this spontaneous flow of solvent molecules, what I am saying, solvent molecules from low concentration solution to high concentration solution. So from where to where it is moving? The flow of, this is spontaneous flow of solvent molecules from low concentration, dilute, or you can say low concentration this side, this is high concentration, this is high concentration, okay. So now what happens? The flow of solvent molecules from low concentration to high concentration is taking place spontaneously. Okay, so during this process some pressure is created over this side towards this high concentration side. Okay, right. Let me completely finish off this so that you will get a complete idea on this. Okay, again I will explain that again. So this SPM is there now, this semi-permeable membrane is there now. It has a special property to allow only solvent molecules, but it won't allow solute molecules. What I am saying, it will allows only solvent particles. What is the solvent here? Water. Here also it is water. So movement of solvent only takes place, but not the solute particles. I hope it is clear. So whatever the solvent here we are using, that particles only move this side. Okay, but not the solute. Why I am repeatedly saying this? I will show you one question based on the understanding of duty of SPM. Okay, right. And one more thing. Now what I am saying, when these solvent molecules move from this dilute or low concentration side to high concentration side, so some pressure is created here. Okay, now what I am doing is, in order to stop this osmosis process, I am applying some external pressure. Generally, if this container is placed in the atmospheric level, like in the classroom, or you can say on the bench. Okay, so this is at room temperature and normal conditions, standard conditions. Now what I am doing is, there will be already some external pressure both sides, that is equals to 1 atm we know. Okay, so along with this atmospheric pressure, now towards this high concentration side I am applying some pressure. So that pressure is called osmotic pressure. Now what is osmotic pressure? The minimum external pressure that is applied to stop this osmosis process is called osmotic pressure. So what I am saying, the minimum pressure applied to stop osmosis. Okay, that is indicated with symbol, osmotic pressure is indicated with symbol pi. Okay, so now what if we apply more amount of pressure, more pressure here this side? See, for example, 2 atms of pressure is required to stop this osmosis process, but I am applying some 5 atm pressure, I am applying this extra pressure. So now what happens? Now here reverse osmosis is taking place. It means what? Now the solvent molecules will move from this high concentration side to low concentration side. It means this process is called reverse osmosis. So where we can use this reverse osmosis in our daily life? Yes, for purification of water. We are seeing now RO water plants. Now what happens? It is a non-spontaneous process now. So one side that high pressure is applied. It means, for example, if this is a impure water, I am taking a salt water or sea water I am taking here. So if this is a sea water and this is normal water we have. So sea water, what happens? Initially osmosis means this water from here, from pure state to this side, spontaneously it might move. Right now, that is what osmosis. But I am applying some external pressure this side, on this high concentrated sea water side. Sea water is concentrated now, it will be having some NaCl, impurities, salts will be there now, minerals will be there now. So I can say these are having some concentration here. So when we apply this pressure, extra pressure, this extra 3 atm of pressure, okay, so the solvent molecules, what is our solvent molecule in sea water? Our water only now. So this water, the solvent molecules will move from here to here. Okay, so this is how we can use the reverse osmosis technique for purification of water. Hope all the concept that we have discussed here is clear right now. And now sometimes in the exam they may ask what are the types of SPMs we have. So we have two types. One is natural and one more is artificial or synthetic. Okay, so natural you can say pig's bladder, pig's bladder. Okay, and the next, when it comes to artificial, you can remember copper ferrocyanide. Okay, these two things you can remember. In the exams they may ask based on this also. Okay, right. Cellophane, all this comes under artificial, but this is one of the important one, that's why I mentioned that especially. Okay, and the next part here you need to discuss is this osmotic pressure is there now. It depends upon the molar concentration of the solution. So if more concentration, more will be the osmotic pressure. So I am writing this, what is this Cm means? It's a molar concentration, that is nothing but molarity of that solution. Okay, and osmotic pressure is also directly proportional to temperature. If temperature is increased, osmotic pressure also increases. Okay, so by combining these two, what we can get, pi is directly proportional to molar concentration and its temperature, right? So I can replace this proportionality with some constant. Here we can use R, that universal gas constant, you can use R here, or it can also be indicated with symbol S, SCMT. Okay, so what is the values for this constant S? S can be represented with R also, right? So now I am saying it will be 0.082 liter atm Kelvin inverse mole inverse. You can use this constant while solving the question. See, generally osmotic pressure means we will be calculating in terms of either ATMs, I mean atmospheric pressures, or in bars, right? So you can use this for atmospheric pressures, or you can say 0.083 liter bar Kelvin inverse mole inverse if you want to calculate in terms of bars. Okay, that's it. Now let me give you few more examples here. See, now if the osmotic pressure of two solutions are equal, we can call them as isotonic solutions, pi 1 equals to pi 2. And in some cases, osmotic pressure of one solution will be greater than the other. Right now, pi 1 will be greater than pi 2 here I am saying. So the one which is having greater osmotic pressure will be called as hypertonic solution. What is that? Hypertonic. Okay, and one which is having lower osmotic pressure is called hypotonic. This is hypotonic and the higher one is hypertonic. And if they both of them are equal, you can call isotonic. I hope these three terms are clear. Isotonic, that's it. These are the three terms you should remember. Whenever there is blur, please inform in the chat box. Okay, right. So I hope up to here everything is clear. Let us see one or two questions so that you will get complete clarity on this osmotic pressure concept. Look at this question. Again, this is from 2023 EAPCET paper, right? I hope question is visible in the screen, I mean without any blur or anything, right? If you want, I can zoom it out. Right, tell me what could be your answer for this. What is the osmotic pressure pi of 0.02 molar aqueous solution of glucose having temperature at 300 degrees Celsius? Okay, so you can simply write CmST, okay, or RT. Okay, see they mentioned R in this question, so you take it as R. Okay, that's it. And next what I am saying here is osmotic pressure also depends upon number of solute particles now. So it is mandatory to introduce Van 't Hoff factor I. So what is this? Now pi will be equals to I Cm RT we got. So right, after this what we can do? Pi will be equals to whether the given solute is non-electrolyte or electrolyte. It's a non-electrolyte now, so I value will be 1. Okay, 1. That's it. And what is the molar concentration mentioned? 2 into 10 power minus 3 and minus 2. Okay, what is the R value given? 0.082 liter atm Kelvin inverse mole inverse. Okay, what about temperature mentioned? 300 Kelvin. That's it. That's it. You can just simplify this, you will get some of these options. So here it will be pi equals to 0.492 atms. Okay, that's it. So option B will be your perfect answer for this particular question. Okay, right. I hope everything is going smoothly here right now. Right. Let me give you one more question. Yes, answer me this. What I told you, there is something called cryoscopic constant Kf in case of depression in freezing point. Right now, depression in freezing point B1. And one more is called elevation in boiling point or ebullioscopic constant in case of ΔTb. Molar elevation constant, or we can say it as molar elevation constant or ebullioscopic constant, that is Kb. Okay, this is 3A3. Next, Henry's law is used to give the relation between solubility of a gas and its pressure. That's it. Okay, so C4, we already discussed very clearly what is Henry's law and their questions also, right? Henry's law and their questions are properly discussed in the last sessions. And next, one more thing here is Dalton's law. Total pressure is sum of partial pressure of the components. Yes, so D is 2. It means if I have a mixture of gases here, gas 1, gas 2, gas 3, like this, I have different number of gases here with their own pressures. So total pressure of this gaseous mixture will be equals to pressure of gas 1, partial pressure of 1, partial pressure of 2, like this, P3, so on. This is what the Dalton's law says here. So yes, A3 is B1, C4, yes, option C will be your perfect answer for this question. Hope clear right now. Next, let us move forward. Yes guys, can you answer me this? Yes, anyone can answer me this question. What they are asking, which are the following substances show highest colligative property? See, I just told you colligative properties directly proportional to their molar concentration of the solution multiplied with its Van 't Hoff factor. Okay, right. So in all the cases, molar concentration is same. Now only the factor here deciding is Van 't Hoff factor, I. So more I value, greater is the colligative property right now. So here how many ions will be obtained? This is strong electrolyte. We can get 3 ions, one Ba+2 and 2 Cl-. So 3 ions. And this is a non-electrolyte. We have only 1 ion, one particle. Okay, AgNO3. So it will give 2 ions, Ag plus and NO3 minus. The next, ammonium phosphate. Here we have 3 ammonium ions plus 1 phosphate ion. Okay, so total ions will be 4 here. So more the number of ions, more is a Van 't Hoff factor, more is a colligative property. So what will be the answer for this question? Option D will be a perfect answer. But if I ask you the order also, you can easily answer D greater than, A greater than, B greater than C. This will be the order of the colligative properties, increasing order. This D will be highest one and this is lowest, decreasing order of colligative properties. You can arrange in this way. Okay, right. Now simply I will give you one relation, use this relation for finding the answers. See what I am saying, whenever you have colligative properties are there. So more the I value, greater is the colligative property. It means RLVP, ΔTb, ΔTf and osmotic pressure. All these things directly proportional to I. If greater the I value, greater is their colligative property values. Okay, and along with this, elevation in boiling point also directly proportional. If boiling point elevation is there, solution with boiling point with greater boiling point for a solution means this is also directly proportional to I. So more the I value for a particular concentration, greater is its boiling point of the solution. And when it comes to freezing point, this freezing point is only one factor here which is inversely proportional because it is minus of I. So more I value, lower will be the freezing point of the solution. So this one thing you should remember, all these are same. Okay, right. So now based on this, I will be giving you one question. Can you answer me this question? Yes, I know you can easily answer this, right. So answer me the questions which I mentioned here. The data is provided here with yellow fonts and these are the 1 to 4 questions that I am expecting answer from your side. Okay, so anyone who is watching this can answer me. Right. Anyone who is watching this can answer me. What will be your answer for the question? Right. And if you want to get the answer, you can just try and you mention your answers in the chat box. Definitely I am going to look into it and I will make it correct if anything wrong is there. Okay. Yeah. I hope if you follow the session properly, you will definitely answer this kind of questions without any confusions. Okay. Right. Okay. So if you like the content, just click on the subscribe button and also share with your friends, those who are preparing for upcoming EAPCET, NEET or JEE exams, or with your juniors also. And you can mention your feedback in the chat box. Okay. So thank you for watching. Stay connected with us. Thank you.